All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you have all had a great weekend. The weather was great. It was amazing yesterday. I got out for a bike ride, and it's been quite a while since I've been out for a bike ride, and it was just really, really nice to get out for a bike ride. I live in this area of the city that's called Unicity, and I bike kind of around the area in the wintertime, and there's this path called the Yellow Ribbon Trail, and it goes along pretty close to where the airport is. If you're familiar with Ness Avenue, there's this big stretch where there's this wide open field, and there's a Tim Hortons right in the middle of this thing. And there's a bike path really close to this chain link fence where basically that's where the runway is for planes to land. And it is a wide open field, and when it's like blowy snowy, it just fills in the bike path immediately. And when I went out yesterday, I actually passed the snow clearing machinery at one point, which was cool to see them actually out doing it. But when I got to that point, this is no word of a lie, it was like going through a hallway, like a corridor, because the snow was just like 4 feet high on either side of me as I'm biking through this. But like importantly, I was able to bike through it. There was a path. I could bike through it, and it was great. So that was really, really nice. I was really happy to get out for a bike ride and like get out and enjoy the weather. Let's talk about operating system stuff. Today, we're going to be moving on from file systems, from like the basic idea of file systems. We've spent quite a long time talking about file systems. We've got several file systems like under our belts at this point. We have this idea of this abstract file system, vsfs, and we have two real file systems, ext2 and exFAT. I'm much less interested in ext2 for clarity because of how similar it is to vsfs. We're going to just treat them as though they're the same thing. So whatever's in the textbook in terms of vsfs, that's enough. Like, I don't really need you to tell me in great detail about the kinds of things that are in an ext2 inode, because it's the same thing as what's in vsfs in terms of our textbook. In terms of our other file system, exFAT, well, you're spending lots of time working on that right now. And we'll kind of keep looking at that as questions come up for the assignment. Like I said last week, I'm going to make time about 5 to 10 minutes in the next 2 Friday classes for just open question period about the assignment. So if you're not able to make it to my office hours, or you're not able to make it to Khaled's office hours, that would be a good time to be asking questions about the assignment. Today, we're going to move on to file system checking and journaling and RAID. And specifically today, what I want you to be able to do by the end of today's class is choose an appropriate RAID level given requirements. So I'm going to be basically describing to you, here is this contrived situation. Which RAID level would be best for this situation? So there's going to be different needs that these people that we're going to imagine will have. And the questions that I'm ultimately going to be asking you are, should they do RAID 0, RAID 1, RAID 4/5, or something else entirely, given the circumstances and the requirements that they have. The other thing that I want you to be able to do, and that's actually kind of related to this first one, is compare and contrast RAID levels. So given somebody's requirements, you should be able to explain to them why they should choose this specific RAID level and why they shouldn't choose the other RAID levels. What rationale should they not have or what rationale do you have for not having them select those things? Before we get to that, though, there was a couple of things that I didn't get a chance to talk about last week about the assignment that I do want to assess, or I want to get to talking about, because in my office hours this morning, there were a couple of questions that people had. So I want to make sure that I'm addressing these broadly before we get too far into it. The first thing that I wanted to bring to your attention is in the assignment document itself. So this is just what's posted on the course webpage. I'm going to scroll way down here to the evaluation part of this. I wanted to talk about this on Friday, like I said, but kind of just ran out of time. The way that you're going to be assessed on the assignment is really based on the functions that I'm asking you to implement themselves. I'm trying to give you some detailed description of the levels that you're going to be assessed at and approximately what your code should be able to do to reach that level. But I do want to kind of like have this reservation that the grading team does have some latitude to move scores, even though you may have achieved some level. They may be moving your score up or down based on different criteria that they have. The first thing that we're assessing is the NQP mount function. And the NQP mount function has some basic stuff that I want you to do, like you have to open the file, and then you have to probably change some file scope variable. And then having some minimal design by contract and defensive programming things. So checking for null, checking that the output that you're getting from open actually gives you a file descriptor, for example. That's the sort of thing that I'm looking for here. As we go up, though, I'm describing in more detail specifically what I want you to validate about the file system image as after you've opened it. So checking that main boot sector for things like the file system name should be the symbols exFAT space, space, space. Exactly that string should be what the file system name's value should be. Must be zero, should be 53 bytes of zeros. It should be 53 consecutive zeros. The first cluster of root directory, when you look at the exFAT documentation for this property, for this field, it tells you about what the minimum value can be and what the maximum value can be. And you should be checking those things when you're mounting your file system to say that, yes, this is actually a valid file system. Level 2, the one above it, is checking the boot signature field and checking the boot signature field, and that's the only thing that you're checking. Each of these kind of build on each other, so as you're getting to one level, you should be accomplishing this to get to the next one. So to accomplish level 3, you should be meeting all or most of the criteria for level 2 and so on. The NQP function, open function, has similar kind of structure. So like you have done some basic stuff in terms of doing defensive programming and design by contract, but then getting to the point of like you can find the root directory, or you can respond appropriately when the file name is not found. So if I ask for a file name in the root directory that is not in the root directory, you should say file not found as a return code from this. To get to level 2, what I'm looking for is you're able to do that, but then you're also able to find things that was not helpful within a subdirectory. So not just in the root directory, but files that are contained within subdirectories with the restriction that you don't have to worry too much about going between clusters for the root directory structure. You can just focus on building something up that is contained entirely within a single cluster without having to build a cluster chain for that. As we go to the top level here, this is level 4. What I'm really looking for is you can build effectively an open file table for your implementation. So you're able to respond to multiple open files at the same time and getting data from multiple open files at the same time. At the same time, meaning like I call open on one file descriptor and then I separately call open, I call open on one file descriptor and then I separately call open on a different file descriptor. Not literally at the same time, but I should have 2 entries in my open file table or more entries in my open file table. NQP read is similarly described in terms of its structure, contained within a single cluster up to multiple clusters and then into reading from multiple different files. The way that I've tried to structure this is that you don't necessarily have to fully implement the open file table to be able to get points for NQP reads. You can do the assumption that I can only open one file. That's fine. Then you can move on to read and start implementing it for only one file, and then kind of go back to open and start adding the open file table stuff separately. The dents function, again, is similarly structured here in terms of trying to build it up as opposed to having to do the complete thing right from the get-go. The other thing that I wanted to bring to your attention was this README in the volumes document. This was getting to be the end of class, and I'm forever apologizing for trying to cram stuff in at the last second in class. So please forgive me for that. I'm never going to get better, but please forgive me for doing this each time. the volumes that I have here, I think that there's still one that I want to add to this, and that is to have one root directory that has 2 text files in it. That's the thing that I want to add to this, but I'll let you know when I actually add that. But the part that I did want to bring to your attention was 2 parts. One, this one image that's called onebigfile.img. This is an important note here. The file in this volume may not have a cluster chain. This is a file that will consist of more than 1 clusters. It takes more than 1 cluster because it's bigger than a single cluster in our volume. But because there were no other files on this when I put this file on the volume, the entire volume is free. And that means that it's able to, the driver, the exFAT driver, is able to say, okay, all of these clusters are free that are right next to each other, that are big enough to fit this whole thing. So I'm just going to put them in all these contiguous clusters. This no fat chain property that's contained in this general primary flags field, if this bit is set, it says there is no fat chain. You don't build a cluster chain from the fat. You don't have to build a cluster chain from the fat. And if you try to build a cluster chain from the fat, you might find that there isn't actually a valid cluster chain for this thing. If no fat chain is set, what you are able to do is look at the start, the first cluster. There will be a valid first cluster for this file. Look at the file size and then just read, starting at the first cluster and just keep going because they're all right next to each other. All of the clusters are immediately right next to each other. The other thing I wanted to point out was down here, the part where I'm describing approximately how you can go about making more volumes if you want to. If you're using a Linux machine or if you're using the Windows subsystem for Linux, you might have to install a package that's called exFAT progs, exFAT progs, to have access to the makefs.exFAT program. If you're using Mac OS, you may actually be able to, and I'm looking for people that have a Mac OS right now. Do you have this repository on your system right now? Do you have this repository in your system right now? What I'm going to ask you to do is just double click on this .img file and tell me if it opens it or if it mounts it to your system. It's a tiny race for all the people who have Macs right now. Okay, it's okay, it's okay. I'm pretty sure, I don't have a Mac to test this right now, but I'm pretty sure. Yeah. It would be something similar to this, yeah. Okay, so yeah, I thought this was the case. If you're running Mac OS, you can just double click on these files that are in this repository and it will mount them and you can read them in Finder, and you can also drag and drop files onto them from Finder. So you can change the existing images if you don't want to go through the process of installing something like Lima to make more images. You can just take the empty image that I've got and then add files to it. That would be another way to work with this on Mac OS. All right, so like I said, I will save time for questions on Friday, but I also have office hours on Wednesday morning, and then Khaled will also have office hours on Tuesday and Thursday this week. So there's going to be other opportunities for you to be able to ask questions about the assignment. All right, so let's talk about RAID. Today, our primary focus is going to be RAID, and then throughout the week, we're going to be taking a look at journaling and file system checking. The first thing that I really want to do is just take some time to verbally remind you of the different RAID levels. Yeah? Okay, awesome. Thank you for confirming that. So it definitely 100% works. And I'm just saying to the camera right now that I'm looking at you, but I won't say who you are. Yeah. Okay, so RAID. I want to verbally remind you of the different RAID levels. There are 3 that we really care about here. RAID 0 is called striping. And this is where you have a bunch of disks and you turn that effectively into one big disk. So the size of each of the disks is just added together and you get one giant disk that's the size of the sum of each of the disks that are in that RAID. RAID 1 is called mirroring. And this is where instead of taking all of those disks and making them look like one big disk, you're taking all of those disks and duplicating the data across all of them. Every drive in the RAID has exactly the same data on it. And so the size of this RAID array, the array of disks that we have, is going to be equal to the size of one disk. So as opposed to the whole thing added together, we get just one, but all the disks have exactly the same data on them. RAID 4 and 5, they are effectively the same. They're effectively the same. There's a small change between RAID 4 and RAID 5. But the basic idea is, instead of sacrificing all of your disks as duplicates, you sacrifice one disk worth of data to calculate parity bits. And the parity here is, if I have 3 4 terabyte drives, I'm going to put data on drive 1 and drive 2, and then I'm going to calculate the XOR of the bits that I've just written to drive 1 and 2 to say this is what the parity should be. So each bit then I'm going to be able to figure out whether or not it's the thing that I expected it to be when I pull it back off of this thing. The difference primarily between 4 and 5 is this idea of rotating parity. So RAID 4 is it's always on this disk, and RAID 5 is let's spread these parity bits across the disks as we're going. Let's do a little quiz. Oh no, oh no, oh no. Don't look at it. Don't look at the answers. Don't, everybody avert your eyes. Don't look. Everybody's going to be really honest and pretend they didn't see that, right? Yeah, okay, thanks. I believe you. I 100% believe you. I'll give you 30 more seconds to join. All right. Our first question is about file systems. Let's kind of wrap it up here. This is a bit of a think about it question in terms of the data structures that we have with these 2 different classes of file systems. All right, nobody saw the answer to that question. Okay. So let's think about this though. Let's think about this. The kind of like constraint that I put on this question is for less than 15 blocks or clusters. Again, clusters and blocks, remember, they mean the same thing. They're functionally the same idea. They're just different words to describe the same idea. With vsfs and ext, what we saw was there's this idea of these direct block pointers. And our direct block pointers are limited to 15 or 16, some very small number of direct block pointers. And these are contained entirely within one single inode. If I were to read a file that has fewer than 15 blocks from ext2, I would need to read the inode, and then I could start reading all the blocks of data from that because I have all of the blocks. With exFAT, we don't have an inode structure. We've got the FAT. The FAT is able to help us reconstruct these chains, but to reconstruct the chain, I have to find the first cluster of this thing and then navigate through the FAT to find all of the clusters, assuming that that no FAT chain bit is not set. Let's just add that here. This is not going to be contiguous things. In order for me to build up this chain to begin with, I have to actually go through the FAT and build that whole thing up. This is going to be a really small thing. If my file was actually going to be just 15 blocks, so like less than a megabyte in size, it's not going to take much time to read that. But if we scale this up over lots and lots of tiny files, over and over and over again, reading from ext2 or vsfs overall would be faster because I can load the inode and then I have direct access to the blocks and can immediately start accessing data. With exFAT, for every one of those files, I'm going to have to go through the process of building up this cluster chain from the FAT. So even with really, really small files. Are there any questions about that? Does it make sense to everybody? And it's not just because we saw that the first answer was the correct answer? Okay, good. I like this question a lot. I like this question a lot because it makes us think about and have to be able to describe what kinds of operations have to be done to the data structures that we have in our file systems when we're doing things like reading stuff. I like this question a lot. Yes. Okay. Here's the next question. Now we're going to ask questions about file system checking, journaling, and RAID. Okay, awesome. I mean, I'm a little disappointed that we didn't pick ridiculous array of itsy bitsy drives and regular arguments on identifying dolphins, but yeah, so like this is a superficial, super high level question, but yeah, good. Here's the next question. Okay, all right, awesome. So again, I super do not care about the actual formulas that you'd use to figure these things out. I super do not care about those things. At a really high level, what I'm interested in is the actual measurements here. So performance for sure was one of the things that we were trying to figure out. How fast can I get data off of this? And how fast can I write data to this set of drives? Different RAID levels have different properties about this. So RAID 0, for example, has different performance characteristics than RAID 4 or 5. RAID 4 or 5 is doing different things than what RAID 0 is doing, so it has different kinds of performance characteristics. Capacity, I'm glad that nobody picked this. Capacity is 100% one of the things that we're trying to measure about sticking a bunch of different disks into this and how much space am I getting out of it. Reliability was definitely one of them, and that was kind of like, it's a trade-off that I'm making to try and decide how much I'm able to recover based on how much I'm able to lose. But the one thing that really doesn't fit here is density. Capacity and density are importantly different from each other. Capacity is just how many bits can I put in here. Density would be like, how many bits can I fit into this many cubic centimeters? And that's not the question that we're trying to answer here. So good, I'm really happy that lots of people are picking this. Simba. Okay, congratulations, Simba. None of you are old enough to have ever seen The Lion King when it was new. I'm sure many of you saw The Lion King. Of course, I have to add this to say it's like, you know, the animated Disney movie with Jonathan Taylor Thomas, who none of you know, but yeah, okay. The live action one, I never saw it. Don't? Okay, okay. I'll keep my childhood memories intact. Okay, here's another question. We've got 2 more questions, and then we're going to move on. All right, okay, so yeah, absolutely we can. Absolutely we can. And the reason that we can lose the parity drive without losing data is if we only lost the parity drive, we can recalculate all of the XORs, all the checksums, all the parity bits that we had from that. If we lose a data drive, we're able to recompute what the data was using the parity bits. If we lose the parity drive, we can just recalculate the parity bits. RAID 5 is kind of taking advantage of this idea. RAID 5 is scattering all of the parity bits across all of our disks, and that allows us to also lose one of those disks, depending on how many parity drives you've allocated. RAID 5 takes advantage of that, and we could lose any one drive and then recalculate what the contents of that drive are based on the parity bit. So yes, absolutely, we could lose the parity drive without losing any data. Okay, awesome, yeah. Now, the important part of this question is when we detect data corruption. RAID 1 allows us to detect that we have corruption because one of our disks will be different from all of the other ones. RAID 0 would let us detect data corruption, maybe, but we have no idea what the actual value should be because we've just scattered all of our data across all the drives. Special file systems here, this is another one that is correct. So something like ZFS with this idea of checksums on the data that we're writing to the drive when we're writing it allows us to detect that this has happened. And then depending on how we use this file system, ZFS, for example, can do things like software RAID. It's able to take many disks and be able to do similar things to what we're able to do with hardware RAID. But RAID 1 to me is the best and most correct answer here. So good, that's awesome. Here's the last question that we're going to have for this quiz. Oh gosh, I made that type, excuse me, very short. I'm sorry about that. It says the quiz is not open. Well, 2 people got to do it. Okay, so 50% of the class got this question correct, which is really, really good. Well, let me just talk about this then. So when would you choose journaling over file system checking? Remember that the basic idea here is that file system checking is the crash has happened. It's over. It's already done. I'm trying to figure out how to get back to the state that I was in so that I can boot my file system, boot my operating system with this file system again. Journaling is, I never want to get into that state. I never ever want to be in a state where a crash causes my data structures to be inconsistent with each other. journaling is something that's going to have a cost when we do writes. So if I'm doing a write to my file system, it's going to cost something. File system checking, there is zero cost at write time because it's very much, I'm just going to let it happen. If it crashes, I don't know, I can't back out of this, but I got to write my data right away. So journaling is going to be a good choice for when you have very few write operations. So write once, and then read only or read heavy. Reading doesn't cost anything with journaling. Writing is what costs us. And all these write heavy options here, these are the kind of like the non-options here. All right. So I'm kind of wondering now how this changes the output because only one person was able to answer that correctly. All right. Congratulations, SUIIII. Congratulations. And I'm sorry to everyone else, I guess, who got kicked out of the quiz before this was able to happen. All right. I'm actually going to come back to this. So if you are currently connected, don't, I've just ended it, so it's going to kick everyone out anyway. We're going to come back to this in just a minute. What I'd like to do is, the textbook does a great job of describing RAID, but then it never actually shows you a RAID controller. And I think that's a valuable thing to take a look at here. So I'd like to show you all a RAID controller. And I want you all to note that this is an ancient RAID controller that I'm going to show you. A lot of modern main boards, so this is like the big part of the computer that you have inside your system, have RAID controllers built into them. A lot of modern ones do. This one is extra old because it's not just a RAID controller that is a separate card, but also because it's a separate card that uses a connection interface called IDE. And IDE is like what came before the kind of tools that we're using to actually 2 versions before what we're currently using to connect things to our systems. So I'm going to pop over here. I'm going to switch to this big camera, and then I'm going to go here so that in class we can see me. Hello, everyone. And then on the web, we're also able to see this. Again, this is an ancient card. This is an expansion card. This uses something that's called PCI to connect to our main boards. So this expansion card will slot into our main board here. There will be connectors on the main board, and it will just kind of plug into the system like this. This is an IDE PCI controller. So there's PCI, and then all of these are the different ports that we could plug into on this card. And this chip that's right here, if it will focus, if I can hold it slow enough, is our actual RAID controller itself. This is the physical hardware device that's doing all of the translations between, I want you to write to this sector, and then it goes to which drive it would actually go to. The idea here is that with this expansion card right here, our physical system is going to see it as one drive. This entire card will appear to the system as a single drive. This chip that we have here can be configured to different RAID levels. So when our computer is booting up, it's going to start by asking itself, like it's going to interrogate itself and start to ask questions about what's currently plugged into my system, what's currently plugged into me, and it's going to be able to recognize that this is a drive, and it's going to be able to start asking questions to this thing. There's a lot of moving parts beneath this that we're not going to talk about. That's going to be in like a little bit of Comp 3370, and then a lot of like other engineering courses. So unfortunately, you may never get to see this. But the idea is, if I have some drives like these ones right here, these are IDE drives. So when I take a look at the back of it, there's like an input port here that's the same shape and size as what we have on this card. The idea is that I can plug these IDE cables into this drive, and then I can plug these IDE cables into this card. The RAID controller then is going to take this card, these drives that are currently attached to it, if I could get it plugged in. Oh no, the pins are bent. I'm never going to be able to use this RAID controller again. There, good enough. I'm going to plug these in. This has got a really important data on it, by the way. I'm going to plug these in to my card here. And my card is going to be responsible for taking these physical drives and hiding them from the operating system. So when my OS comes up, it's going to see one drive, and it's going to see it on this card. This card is going to have the responsibility of saying, okay, I've been issued a write command. Now I need to decide which drive to actually put it on. I've been issued a read command. Now I need to decide which drive to read it from. There are problems with this. The primary problem being that each one of these little chips here, if you have the same chip from the same vendor and this card dies, the only way to get data off of these drives is to get the same card again. You cannot take these drives that have been attached to one RAID controller and then just plug them into a different RAID controller. The other RAID controller has no idea how this one works internally. It has no concept of how this one works internally. I'm going to pass these around if you want to take a look at them. This does not have actually important data on it, just to be clear. These drives are 160 gigabytes and 120 gigabytes in size. Please just make sure it makes its way back up to the front at the end of class. So I'm going to pop back over here, go back to this scene, and I'm going to go back to my web browser, and then I'm just going to pause here to see if there's any questions about RAID controllers.
So when you're plugging it into a new controller, you're not able to just manually tell it what kind of RAID the old one was using?
So the question is, so this is the assumption that the RAID controller itself dies and we have to plug it into a new one. And the question was, can we not just tell it what level of RAID it was at? And you might be able to, but the problem isn't even what level of RAID it is. It's that whole idea of logical and physical addressing between the RAID controller and the actual drives. So remember that when our operating system is making a request to write to a specific sector, from the operating system's perspective, this is the sector that's going to get written on this one big drive that our RAID controller is presenting to us. The RAID controller itself is taking this as a logical write. So it's trying to say, okay, if I take that sector, I have to map it to this disk. And that mapping might be made as a hard-coded table in this piece of hardware, like actually in silicon. Other RAID controllers wouldn't necessarily have exactly the same mapping structure that this one currently has. So even if you could say, well, all these drives should have the same data because it's RAID level 0, we don't actually know if I wrote sector 0 on this drive, if it actually goes to sector 0 on the physical drive. My RAID controller might do something weird like put sector 0 at the end of the disk. It's up to it to do stuff like that, to make decisions like that. Any other questions? All right, okay. So what I really want to do here is I want to spend some time taking a look at some different scenarios. And I want you to be able to make decisions based on what you know about what RAID level we should be selecting for this. The document that I am going to read aloud to you, this is going to be like a story time with Franklin sort of situation. The document that I'm going to read aloud to you is posted on the course webpage. So if you want, excuse me, to have access to these scenarios, or if you want to do a better job of reading it in your head as opposed to just listening to me, you can find this on the course webpage as a Word document right now. And then what I'm going to do is I'm going to pop back to Mentimeter and I'm going to ask you again, what RAID level is the right RAID level for this situation? And your options are always going to be RAID 0, RAID 1, RAID 4/5, or something else. Those are what the 4 options are going to be. I don't want to do things like having to worry about RAID 0/1 or RAID 1/0. That's not something I'm concerned about right now. I'm thinking more of just the basic RAID levels that we've seen in the book. So the first scenario that I want to tell you about is the data hoarder. The data hoarder does not describe me literally as a real person, I promise. This is not who I am. I'm going to read this to you. Like I said, this is on the course webpage if you want to refer to it on your own, but yeah, story time with Franklin. So, the data hoarder. I feel like I have a responsibility to provide backup services for the good of the wider world. I like to back things up like the Expanse series 1 to 6, and I only back up 4K Blu-ray rips for the greater good. For the greater good. This data is sort of important to me, and this actually literally is me. Me, Franklin. I really love this book series, and I really love this TV show. If you're into hard sci-fi, this is a good book series to read. It's called The Expanse. But the backups take a lot of space, and I teach computer science at a university, and I don't make a lot of money, and so I can only afford to buy lots of really small disks. So just imagine in your mind's eye that I can only go to the store and afford to buy 250 gigabyte disks. Or alternatively, I can only go and dumpster dive 250 gigabyte disks, and that's all I can afford to get. I can't afford these big disks like the 16 terabyte disks that are out there now. I think there's up to 22 or 24 terabytes. I'm aware that there's lots and lots of other people that are backing up the same data, again, for the greater good. So I'm not actually too concerned if I lose this data. I'm not actually too concerned if I lose it. It's just going to take me time to get it back again from the backup service that is the internet. Which RAID level would be the most appropriate for what I have right here? I'm going to pop back over to Mentimeter, and I'm going to pop this up. And we're going to start from here. If you do pick something else, I'm going to politely ask the room for that person to self-identify, but I don't expect anyone to actually self-identify if they don't want to. I'll give you about 10 more seconds to answer the question. Okay. All right. RAID 0, I 100% agree with you on this. Yes, I 100% agree with you. And then RAID 4, 5 would be my second choice. Yes, this would absolutely be my second choice. The main caveat here is that I can only afford to buy or dumpster dive for 250 gigabyte disks. That's all I can get. So they're really, really tiny. And like one season of this show, and I'm telling you this not from experience, I promise, is like tens and tens of gigabytes. It's a big thing when you're actually getting these 4K Blu-ray rips from the internet. They're really big. No, I'm ripping them from my own disks, I promise. RAID 0 is going to give us the most capacity. So if I got 10 of these 250 gigabyte drives, then I would have a total of 2.5 terabytes, which wouldn't be very much, but let's say that I got more. Let's say that I got 100 of these disks. Okay, so now I have 25 terabytes. I've got 25 total terabytes. RAID 4, 5, this is sort of important to me. Yeah, this is sort of important to me, but I'm not really willing to lose that much disk space for all these things. So this is sort of important to me, says, I don't want to have to spend the time to download this again, so I will maybe make this compromise of I'm going to lose 1 or 2 of these disks for parity, and then the rest of them are going to be for the space that I've got. RAID 1 is probably not the choice I would make. It's probably not the choice I would make because now I've got all the disks all crammed together, and they all have the same copy of the same thing, and I only have 250 total gigabytes, and that's not going to be enough to store multiple seasons of this show. Something else. So I'll politely ask if you don't feel comfortable, that's super okay. Yeah. RAID 6? Okay, so why would I do RAID 6?
And then it doesn't spread very. So you have a lot of this are small. You only need 2, but you don't lose much data in the other ones.
That's a compelling reason to me to choose RAID 6. So having several parity disks as opposed to just one giving up a little bit more space for this. That's a very fair thing for me to choose, yeah. Any other options? Another reasonable option to me would be software RAID, or to use special file systems like zfs. That's another one that I'm thinking of. Okay, awesome. Okay, the next one is, this is scenario number 2. This one 100% doesn't describe me, to be super clear. The closest that I came to video games recently, like I said, was Stray. And before that, it's like Super Nintendo games. So yeah, keep that in mind. Speed is of utmost importance to me. I bought the fastest disks money can buy. So this is like PCIe NVMe drives, PCI 4. I don't actually know what all these acronyms mean, but you know, they're there. I bought the fastest disks money can buy, but they're just not fast enough. If my friends ever saw that I was running at anything less than 120 FPS, I would be exiled and embarrassed. I know that lots of space is good, but I don't need lots of space, since I only play one game at a time, and I can always reinstall games that I'm not playing from Steam. I obviously have a fast internet connection to go with this. Which RAID level would be appropriate for my workload? I'm going to give it 10 more seconds. All right. My top 2 choices are RAID 4.5 and RAID 1. Those are definitely my top 2 choices. So I'm in agreement with what you have selected here. RAID 4.5 and RAID 1. I'm thinking about RAID 1 primarily because if I've got the same data duplicated across all of these drives, the theory is I can read data from all the drives at the same time. Everything is the same. So if Steam or my video game is asking for textures to be loaded that are bigger than 1 block size, my operating system should be able to issue requests for many of those blocks all at the same time and be able to get them back, in theory. RAID 4.5 is kind of similar to me. We can start to spread this across these disks. We get parity bits. We get some confidence that the data that we're getting off the disk is going to be okay. But for me, my best choice is RAID 1. RAID 0 is my least selected choice here because I don't really care about disk space. I don't really worry about having many terabytes because I'm just going to reinstall a different game later. And so something else. Yeah. Why not just use an SSD? That's what this is going to be a RAID array of, is a RAID array of SSDs. Yeah. But no, that's a fair point. Why not just use an SSD? Yes, yeah, absolutely, yeah. All right, I'm gonna give you the last scenario here. This one's called The Scientist. I'm a scientist working at the science factory, working on important science. These are all trademarked things. The Science Factory is from a book. It's from a book that I read my children called The Investigators. And it's 2 alligators, obviously, who are investigators working at this place called Suit. And they have to go investigate something that's happened at the science factory. I will let you read these books on your own, but they are very good. I have several different needs. I need my important results about my important science to be calculated really quickly. This is urgent. I must get this done now so that somebody else doesn't publish the same results before I do. I need to be confident that the important results that are on disk are accurate in the long term. I don't want to have to retract my important science paper just because I'm not able to get my data back reliably when someone else asks questions about it. I need to be able to have access to lots and lots of very big temporary space while the calculations for my important science results are running. What RAID levels would be best for my workload? I'm going to give you 5 more seconds to answer. All right. 100% I agree with you. My first choice is RAID 4.5. The something else is my second choice here. The something else is my second choice, and the something else here, and this is, to be clear, I wasn't necessarily expecting you to pick this or think about it, but my second choice here is I want to have a RAID 0 array for temporary data. I don't really care about the intermediate results of this stuff. I just need lots of space. I want to have a RAID 4.5 and maybe a RAID 1 array for my actual results, because I need to keep these in the long term and I need to know that the data is stored reliably. So this might be two separate things that we're talking about here, not necessarily just one, but it might be two different things. All right, thank you all for participating in that. At this point, you should be able to choose a RAID level given different requirements. So given a workload description, you should be able to make a choice about the kinds of RAID level or levels that you think that this person should be using. And then related to that, you should be able to compare and contrast different RAID levels with each other. So as part of the decision-making process of you should choose RAID 0, you should explain why RAID 0 and RAID 4.5 are not appropriate choices for this specific workload. That's it for today. I hope you all have a great day, and I'll see you on Wednesday. Bye, everyone.